guys, welcome to another round of chemistry notes. In this video, we're going to be talking about mass spectrometry. We've been talking about average atomic mass and using the percent abundances and masses of isotopes to find the average atomic mass, but someone had to come up with those masses and come up with those percent abundances. Those are measured, so the masses of the elements and the percent abundances of those masses are measured using mass spectrometry. And we normally just abbreviate this to mass spec. Easier to say, shorter, fewer syllables, just easier all around. Mass spec. This is a technique that separates particles according to their mass. Different particles have different masses. The heavier they are, the lighter they are, the more they are separated. So how this works is the material to be tested, whatever you want to find the masses of and the percent abundances of, it is ionized. It's put into this machine called a mass spectrometer, and it's heated up super hot until it is vaporized and then ionized. And once it is ionized, it is separated according to its mass. So this is a mass spectrometer. This is what it looks like. You put your sample in at one end, and there is a heater at this entrance point that vaporizes the sample, turns it into a vapor. So then that vaporized sample starts to pass down this tube, and it gets to right here where an electron beam ionizes it. It turns it into ions, which we haven't really talked about yet, but basically it turns it into charged particles. It gives it a charge. So now it's charged. You've got these charged particles with all different masses, and they keep traveling down this tube, and it passes through these plates that speed it up. So now you've got these really fast charged particles passing through right here where you've got some magnets. And these magnets basically bend our charged particles. Since they have a charge, they are affected by the magnets, and they bend as they pass through this tube. And just like trying to steer something really heavy, like a shopping cart full of groceries, versus trying to steer something very light, like an empty shopping cart, it's easier to steer the light particles. So they bend a lot, and they end up way down here at this end of the detector. And the heavier particles are harder to steer, and they barely bend. They kind of keep going in a straight line, and they hit this end of the detector. And as a result, you get all of these different lines of different masses hitting the detector. And the readout, what you actually get as a result, is called a mass spectrum. It looks like this. So this is a mass spectrum. And each of these lines in the spectrum is called a peak. Each peak comes from one of those masses hitting the detector in a different spot. So each peak represents a single isotope of a single element. Each peak represents one mass. Each mass gets its own peak. The location of each peak on the x-axis indicates the mass of the isotope. So heavier things with a higher mass, will end up over on the right because they did not bend as far when they passed through the field. And lighter things with a lower mass, will end up on the left. The intensity of each peak, which is indicated by the height of the peak, indicates the relative abundance. So this peak, the taller one, has 100% abundance. And then this shorter one has, I don't know, maybe like 90%. And it's called a relative abundance because it's relative to each other. The tallest thing will always be 100, and then any of the shorter peaks are relative to the tallest one. So this one is almost as tall, it's maybe like a 90% as tall, so we say it has 90% intensity. If you had something like this tall, that would be like, I don't know, 10% intensity, 20% intensity, because it's 10% of this tallest peak here. So that's the relative abundance. When we were doing our calculations for average atomic mass, we were using percent abundance, but we can use our relative abundance, we can use our intensity to find percent abundance. So to determine the percent abundance from the intensity, from the relative abundance, the total intensity, the total percentage, must be normalized. it has to be made to equal 100%. If we look on our last slide, here we had 100%, here we had like 90%. Well, 100 plus 90 is 190%. That's not how we know percentages work. So we want to take all of our intensities and make them add up to 100. And we do that using this formula here. To find a percent abundance of a specific isotope, you'll take the intensity of that isotope, divide it by the sum of all of the intensities of all of the isotopes, and then multiply it by 100. You'll have to do this for every isotope that you encounter. And when you're done, all of your percent abundances of all of your isotopes should add up to 100, right? That's how you check yourself. Do your normalization process, use this equation for each of your isotopes. When you're done, take all of your abundances, add them up to 100, and if they don't add to 100, check your math because something bad happened. On the flip side of that, if your abundances already add to 100, don't do this step, right? Don't make your life harder. Only do this if your percentages are not adding up to 100. This equation is not given to you on the formula chart. You're going to have to memorize this. You'll have to know how to use it, when to use it, and what it is. It will not be given to you. And as always, this 100 is just a result of talking about percentages, right? It's not an actual value, so it's not going to affect our sig figs. So no for sig figs. That 100 doesn't affect anything because otherwise we would always only have one sig fig, and that's no good. So let's see some examples of this. Our first example here says hydrogen has 3 naturally occurring isotopes. Hydrogen with a mass of 1, hydrogen with a mass of 2, and hydrogen with a mass of 3. Chlorine has only 2 commonly occurring isotopes, chlorine with a mass of 35 and chlorine with a mass of 37. The 2 elements combine to form hydrochloric acid. It's made of hydrogen and it's made of chlorine. And that L should be lowercase. That's a typo. It should be HC lowercase l. How many peaks will be present in a mass spectrum of HCl? Well, we saw back on our mass spectrometry diagram that every mass bends a different amount as it passes through those magnets. So we've got 1, 2, 3, 35, and 37. If we go back here, we can imagine each of our masses passing through. So we had a mass of 1, 2, 3, 35, and 37. Well, as they pass through this magnetic field, the mass of 1 is going to be really influenced by this magnet, and it's going to bend way over here and give us a line way down at one end. 2 will bend just a little bit less, 3 will bend less, and then 35 and 37 will not bend nearly as much. So 35 would be like here, and 37 would be like here. So since we're putting 5 different masses into our mass spectrometer, we're going to get out 5 different peaks, 1 for each mass. Every individual mass gets its own peak. Each peak represents an individual mass. All right, so this was a problem that didn't even require us to do math. You will encounter problems like this, but you will also encounter problems that do require you to do math. So we're going to look at one of those next. Right, here we are given a mass spectrum for an unknown element and told to consider the mass spectrum shown to the right. And a couple of numbers that should have shown up here and didn't. Your tallest peak in your spectrum is always going to be 100%. And in this case, in your notes, it's 100 point. That's important. If you don't see it there, you can assume it's 100 because the tallest one is always 100. The shorter one you'll have to be given. So this was given in your notes, and I just didn't copy it onto the slide. So on your notes, this is 40 point percent. And remember, those decimals are important because if they weren't there, this would be 1 sig fig, and this would be 1 sig fig. But we don't want to do math with 1 sig fig. It gets really imprecise. So we put our decimals there, and now this is 3 sig figs and 2 sig figs, which is a much better place to be. So part A here says to determine the average atomic mass of the element. Well, we're going to use our same average atomic mass equation, but remember that equation requires us to know mass of each isotope, and it requires us to know the percent abundance of each isotope. Well, we know the mass of each isotope. One has a mass of 85 and one has a mass of 87. But if we add up our percentages here, we get 100 plus 40 is 140. And that is not how that's supposed to work. So since they don't add to exactly 100, we are going to have to normalize. And that is going to be step 1. So step 1 is to normalize our abundances. We're going to have to do this once for each mass. So we'll do it for our mass of 85 first. So the percent abundance of our mass 85 isotope is equal to, remember in this equation, it's the intensity of just the isotope you are looking at over the sum of all of the isotopes in the problem. So here, the isotope we are looking at has an intensity of 100 point. So we'll do 100 point percent over the sum of all of the intensities, so 100 point percent plus 40 point percent times 100. We're going to have to solve these through. We're going to do it in 2 steps to help keep track of our sig figs. So first we get 100 point over, this has a significant figure in the ones place and in the ones place. So we're going to keep this to the ones place by keeping that decimal. So over 140 times 100. And then doing our division here, 100 divided by 140 times 100, you get 71.4286%. We are not going to round this because it's not the end of our problem. This is not our final answer. What we are going to do is mark where we would round it so we can keep track of how many sig figs are in our problem. So the last thing we did here was division. We had 3 sig figs and divided it by 3 sig figs, so our answer should be rounded to 3 sig figs. So if we were going to round this, we would round it to right there. We would round it to the 10ths place. So we can write this up here. The percent abundance of our 85 mass isotope is 71.4286 rounded to the 10th place. That's our first abundance. So now we'll normalize our other isotope. We'll do our percent abundance of our mass 87 isotope. That's going to be equal to the intensity there, which is 40 point. So we'll do 40 point over 100 point plus 40 point times 100. So then once again, solving this out in 2 steps, it'll become 40 point over 140 point times 100 is equal to 28.571%. And then again, we are not going to actually round this, but if we were going to round it, this time we had 2 sig figs divided by 3 sig figs, so we would round this to the ones place. So our percent abundance of our mass 87 isotope is 28.571% with essentially 2 sig figs. So now let's clear up some of this mess at the bottom so we can actually answer the question. So getting rid of some of that extra work so that now we can actually answer the question. That is work you would need to show on a free response. We just are out of room. Now we can actually solve for the average atomic mass. So our average atomic mass is going to be equal to the mass of our first isotope, which is this 85, times our percent abundance, which is this 71.4286 divided by 100. Remembering that this 100 is also not really a real number. And then plus our other isotope, which has a mass of 87, times 28.571 over 100. And then we're going to do our math in 2 pieces. We're going to do our first set of multiplication division. We'll do our second set of multiplication division, and then we will add them together. So this first group of math, 85 times 71.4286 divided by 100, should give you 60.714. And your second set of math, 87 times 28.571 divided by 100, should give you 24.7 Once again, these are not our final answer, so we are not going to actually round them, but we do need to consider where we would round them to. So our first problem here, or our first set of math here, we had said we would round to 71.4, which is 3 sig figs. And this 85 is an exact value. When the mass you are using is a straight up just a number, it means it's a counted value. This is counted. It's the number of things in the nucleus. So we're not going to let it affect our sig figs. We're just going to use our percentage, which is 3 sig figs. So we would round this answer to 3 sig figs. We would round it to 60.7. Same thing over in our second set of math. We had said we would round to the ones place, giving us 2 sig figs. This is another counted value, so we're not going to include that. So we're going to round this number to the 2 sig figs, which would be right there. So now we are going to finally add them together. 60.714 plus 24.857. Adding those together, you should get 85.571. And then finally rounding that for sig figs, the last step we did was addition. So when you're doing addition, it matters which place value you are filling. So we did 60.714 plus 24.857. That gave us 85.571, but our last significant place that we could fill was this ones place, was the 4 right there. So we're going to have to cut our answer off behind the ones place. This 5 says to round up, and as our final answer, we will get 86 as our value. And then remember, your units of average atomic mass are AMU. All right, so it's not that different from average atomic mass. It's just one step more at the beginning to normalize, and then it's a lot of weird sig fig business. But the math itself is mostly just algebra. All right, so what we can do with this mass, part B says which element is most likely shown in the mass spectrum given. Well, to solve this, you're going to go to your periodic table and you're going to find the element that has an average atomic mass closest to 86. And if you look at your table, you will find that that is rubidium. We know that it's rubidium because rubidium has a mass of 85.47, which is the closest to the mass we found of 86. So to identify, we would say 86 AMU. The mass we calculated is closest to the average atomic mass of rubidium, because that is that 85.47. All right, at this point, there is some practice in your booklet. There are 3 practice problems. Not all of them require math, so make sure that you read the question carefully, work them through yourself, get an answer, and when you're ready to check your work, go ahead and unpause the video. All right, hopefully this is what you got for your answers. If this is not what you got, then you should go to my website and check the key, because that has the actual work written out to help you find out where you maybe went wrong. If you got these all right, then you should be set to move on to your quest, move on to your easy peasy review, and get ready for your test. So good luck, have fun.